Okay, thanks, Francis. So it was told to me that this is a very informal sort of seminar, and I would like to keep it that way. So please interrupt me whenever you feel interested or want to know something or have any further questions. Don't hesitate to ask. So allow me to preface this talk by saying that it's a little bit intimidating to be talking to all of you about astrophysics and an astrophysical object because I'm a physicist. And although I've been calling myself an astrophysicist at cocktail parties for years, it's only now that I'm actually starting to do some astrophysics, and my history is not there. My own personal expertise in the field of gravitational wave detection is about the detectors. So if you want to know anything about the technology, we're good. Nonetheless, I have presented a talk here which is mostly focused on the analysis and some source parameters that we infer from our analysis. So it's really the astrophysics. And I'm comfortable talking about those things at some level of detail, so don't worry about that. And also don't hesitate to ask questions, because if I don't know, I will not hesitate to punt on an answer. All of the information is in the papers that we've presented, and so let's try and keep this going. Okay, so first off, I want to state that this is all the work of the LIGO scientific collaboration, which is a collaboration of this many institutions. You can see that ANU is up here. That's one of them. And then the Australian participation is through the Australian Consortium for Interferometric Gravitational Wave Astronomy, which contains 6 universities, not all of which I can find here. And I don't know who made this slide, but it's a visual masterpiece, I think. So the LIGO detectors, which detect gravitational waves, are glorified, fancy versions of Michelson interferometers. So I'm sure you're all familiar with Michelson interferometers from the days of stellar interferometry that Michelson did himself. But we've taken it a bit further and added some extra bits. So instead of just ordinary Michelson arms, the laser light comes in and there's a beam splitter that goes to the 2 arms. We add extra mirrors at the input to turn the arms into Fabry-Perot cavities to boost the gain, so the photons bounce back and forth many, many times. And this effectively lengthens the arms of the interferometer to make them sensitive to strain.
Where does that occur?
Where does what occur?
The bouncing.
Oh, so this is a partially reflecting mirror here, and this is a highly reflecting mirror. So photons enter, and then effectively they're stored for a time in the cavity before coming out. And during that time, they build up the gravitational wave signal. And then we add another partially reflecting mirror here in order to recycle the laser light, because when there's no gravitational wave coming by, the Michelson operates on a dark fringe. All the laser light is reflected to the laser, and normally you would dump it and lose it. But Ron Drever had the idea, and Roland Schilling, long before I was born, to put a mirror here and recycle that light. And the signal light, when a gravitational wave comes by, and it's a quadrupolar wave, so it shortens one arm and lengthens the other arm as it comes through, disrupts the destructive interference in the dark port and lets a little bit of light out. And then we detect that, and that's how you get the gravitational wave signal. It's a standard Michelson technique. We also recycle the signal with a signal recycling mirror, so we send it back into the interferometer. It's a little bit more complicated than that. It's not quite so simple as that, but needless to say, this mirror allows us to manipulate the bandwidth of the interferometer independently of storing the power. So the properties of the cavities in the arms, mostly what that does is that tells us how much circulating power. So you see we put in 20 watts of laser light, but 100 kilowatts are circulating in the arms because it's being stored up over time. And that circulating power is what most efficiently converts gravitational wave strain into laser phase, or the optical phase of the light coming out. So you want as much power as possible in the arm. But of course, if you do that by storing it for longer and longer and longer and longer and longer, then now you can't see gravitational waves that are changing at rapid frequencies anymore. So this allows us to decouple those two things, this signal recycling mirror, decouple those two things by shaping how the signal leaves the interferometer without changing how the power is stored in the interferometer. And the LIGO, the observatory, consists of 2 interferometers, 2 of these 4-kilometer Michelsons, one in Louisiana and one in Washington State. And on this, because it's flat, it doesn't look like they're aligned, but they're as close to being aligned as they can be. So and by that I mean this arm and this arm are as close to being aligned as they can be. Yeah?
What's the wavelength of the laser?
1.064 microns, so it's a neodymium YAG line.
Sorry, what does it mean have stored power? I mean, have stored energy.
Yeah, you have stored energy.
So you've got, if you put a detector and you measure the photons going backwards and forwards, that's...
You would be destroying it. Yeah.
But
So
how many kilowatts
It's 100 kilowatts of circulating power. So that means that the field,
Backwards and forwards in the cavity.
that's right, and the field amplitude in here is equivalent to a 100 kilowatt laser. So this is about 1/8 of the full sensitivity. So if you want to do something like calculate the heat load in the mirror, then you have to use this number. If you have a single bounce loss, you use this number for that to calculate the heat load.
Doesn't that change the accuracy with which these photons are in phase with each other? If I keep on hitting the mirror multiple times in slightly different orientation?
It could, yeah. But so the thinking of single photons bouncing back and forth is not how we think of it. We think of it in some stages we think of it classically, and in some stages you have to think of it quantum mechanically because the detector is limited by the quantum mechanics of the photons. But it's a resonant cavity. So if you think of the field coming in, the mirror is lined up such that the input light is resonating with one round trip coming back. And then all the round trips are actually resonating now because the cavity is set to be an integer number of wavelengths of the laser light. So they're all coherent. They're all coherently combined. It's coherent radiation, which I guess is an important fact. So the history, just a little bit of history. Initial LIGO was started in the late 90s, and then the 5th data taking run, which was a long run of a year, happened in the mid-2000s. Then we took it down and made some minor upgrades that we called enhanced LIGO at the time, took some more data at S6, and at the end of S6, that's when we completely started disinstalling the interferometers and putting in what we called the advanced LIGO interferometers. It's called advanced LIGO because you can't call it LIGO 2 because then funding agencies get scared that there will be LIGO 3. And so it's called advanced LIGO. That's all, but it really is LIGO 2. It's a completely different system.
What's the next one going to be called?
LIGO Voyager. Right now, we're calling it LIGO Voyager. The name is not decided, but. And so this dark period here is the time it took us to install the advanced LIGO components. So the advanced LIGO project is this purple bar back here, and you can see that the project began in mid-2008 when we were installing the enhanced components. And this is when the construction began of just bits and hunks of metal that would need to be moved into the vacuum. And at this point, we started uninstalling initial LIGO and installing advanced LIGO. And it took 5 years before we got there. And then there was a very brief period of commissioning. This is amazing to the people in the field how quickly this went compared to initial LIGO, which took like a decade, before we started our first observing run. So the advanced LIGO detectors, I just want to touch on some of the key points. So again, they're Michelson interferometers with 4-kilometer-long arms. The entire arm is evacuated in these vacuum tubes. So it's 4-kilometer, 1-meter diameter vacuum tubes.
How good a vacuum?
Really good. Really good. Better than 10 to the minus 9 torr. So they're UHV all the way. The tubes are never vented. So they were pumped down and baked when they were installed, and they've never been vented since. And then in order to detect gravitational waves, you have to have a mass that is free to respond to gravitational forces nearby. So the way we do that is by having the masses be suspended from pendula. So this here is the test mass that actually senses the gravitational wave, and it's free to move in the transverse direction. It's suspended so that it doesn't fall on the ground. And in order to isolate the test mass from motions of the ground, first off, the pendulum does that because the pendulum has a mechanical response that falls off like frequency squared. So at high frequencies, you're isolated from ground motion. But that's not quite enough. So the pendulum is suspended from another pendulum, which is suspended from another pendulum, which is suspended from another pendulum here. And then this thing is attached to this. Imagine this is upside down. This is a 6-axis isolation stage, and this one is all active. So the pendulum has 4 stages of passive isolation, and this one has 6 axes of active isolation using seismometers and geophones to keep the platform inertial. And then this whole thing is attached to another one of these, like that, and then it's upside down, and that's what you see here. And then those are suspended on these piers, right here, these beams, and these beams are each connected to the piers with more 6-axis actuators for the final stage of isolation. So that's 3 stages of active isolation and 4 stages of passive isolation to get the displacement noise below 10 to the minus 18 or 10 to the minus 19 meters. And then in order in order for the whole thing to work, we also have to be able to push on the mirrors to actuate on them to keep the arm lengths at an integer multiple number of wavelengths. And we do that by having a reaction chain which is also on 4 pendula, because if we just had our actuators stuck to the ground, that would make the mirrors move by the forces on the actuators, the noise in the actuators. So they're suspended from this reaction chain. And those are some pictures of the vacuum tubes. A person is about this tall there, and that is 200-watt single mode, single spatial mode and single longitudinal mode laser that was built by by Laserzentrum Hanover in Germany. It was a partner at Advanced LIGO. So those are the main technological bits. And the noise that we got in the first observing run goes like this. It falls down to a little below 10 to the minus 23 in strain at its peak sensitivity, around 200 hertz. So that's a pretty small number. Everyone has different ways of saying it, but we're all physicists, so it's roughly, 1/10,000th, even better than 1/10,000th of the diameter of a proton in displacement of the mirrors. So the strain is a dimensionless number of the change in length divided by the length. For 4 kilometers, that's 1/10,000th, or even better than the diameter of a proton. So that's how finely we're sensing the displacement of the mirrors. And the point of this curve is to show you that this is a noise spectral density. So it's the square root of the power spectral density of the strain signal coming out of the detectors. And there are some colored bars here to show you how stationary it is that show you the plus 90% variation, but you can't see them. Anyways, it's not so good up here at low frequency, but it's very good here, where we detect most of our signals, where we detect our signals.
What's the big peaks, and why are they different from one to another?
So some of these peaks are known modes of the optics. Some of them are what we call violin modes. So the wires that suspend the last stage are made of glass. So they're roughly, they're different thicknesses to minimize the thermal noise, but they're all less than 400 micron thick wires of glass. So they're basically glass hairs holding it, and they vibrate back and forth like violins. It's really more like a guitar, but we call them violin modes. So many of these are violin modes of those optics. Other lines are calibration lines. So we inject lines in order to known forces in order to calibrate the response. This is the mains line. And then some of these other ones, these are also calibration lines, actually. They're also calibration lines.
Identical pieces of equipment, so why aren't the spectra from the blue and the red identical? There's some really big red ones and no blue, and some big blue and no red.
They're not that identical. They're designed to be as identical as possible, but each interferometer literally has 10,000 parts, moving parts, and there are different teams making them work, and they have different priorities, but they also have different issues in terms of where they are. So the environment in Louisiana is different from the environment in Hanford, and essentially the interferometers are as identical as we can make them, but they're not perfectly identical. Anytime you have two things built by and operated by two different teams, you'll wind up with small differences like that. So going forward, this is how well we understand the noise. So the red is the noise limit of, this is the L1 interferometer, I think, the Livingston interferometer. And the other curves are what the noise contributions should be. So these ones that are clearly not data are theoretical contributions, and this gray one is the sum of the noise that we expect from all of the other degrees of freedom. So those are the angular degrees of freedom of the mirrors, basically, and other length degrees of freedom that are not sensitive to gravitational waves. And you can see that they account for most of the limitation of the sensitivity below 20 hertz. So the limitation in sensitivity below 20 hertz right now is self-inflicted, effectively. And so this is where a lot of the focus of the work is going to be going forward. But then the important thing is that there is also still this gap here. So this gray curve, when you sum it with the blue curve, will start to come together and match the red curve. And so this spot here and a bit of this spot here, we don't know what the noise is at all there. So that's also going to be the focus of our efforts right now. The interferometers right now are not taking data because we're working on these noises in this regime to try and bring them down even further. So you may have heard, we published a paper last week called Observation of Gravitational Waves from a Binary Black Hole Merger in PRL, and so this is what I'll talk about for the rest of the talk. So if you have any more questions about the detector, please now while I'm still comfortable. Yeah.
Are you sure that the mystery noise is in fact noise and not signal from something else?
We're pretty sure, yeah. It's not coherent between the two detectors, so it can't be signal. Yeah.
You said you had these two arms where the mirrors move opposite directions.
Mm-hmm.
Okay, so suppose you've oriented 45 degrees differently. Would you have missed that wave?
Yeah. It depends on the polarization.
So there
Yeah.
is polarization associated with the gravitation.
Yeah, gravitational waves come in two polarizations, and they're oriented at 45 degrees to each other. And if the polarization comes that your detector is not sensitive to, you miss it. And the detectors are both oriented in the same direction, so we're really only sensitive to one polarization with LIGO as it currently stands.
But they're at such different longitudes and latitudes. Do you actually do a lot of Earth moving to get them lined up with the...
No, I think it just worked out that way.
Just live...
They're in pretty flat spots.
Well, but then they'd be looking in different directions.
And also the locations, they are looking in different directions, so they're not perfectly aligned. But most of the polarization sensitivity has been lost, or was not designed for on purpose. And that's because for this first detection, it turned out to be, well, and for any first detection, it turned out to be important. If you have perfectly anti-correlated polarization, so each detector is sensitive to its own polarization but not the other one, it's a real chance that limits your chances of seeing the same signal in both of them at the same time. So, and I just want to point you to our website. If you want more details on anything, it's an easy to remember website, LIGO.org. That's the LIGO Scientific Collaboration website, and it has links to all of the papers. So we published a set of papers. The main paper in PRL came out last week, and that is a nice description of the detection, and I think it's a very well-written paper. And it came with 12 companion papers, which have all of the details of various other aspects, both of the detection and of the detectors. So there are papers that characterize the detectors describe them a little bit more, and then there are papers that characterize the noise, the calibration, and then there are papers that go into deeper analysis of the particular source, which we've called GW150914.
Excuse me, somebody asked me
Yeah.
yesterday why you published the main thing in PRL rather than in Nature or Science. What's the answer to that?
It's a physics paper, and we wanted physicists to read it.
They do allow physics into Nature.
Yeah. We knew that PRL would let us publish the paper the way we wanted to publish it. And PRL has been supportive of the field in the past. So the decision was made a long time ago that it would go to PRL, long before we detected, and not Nature or Science. Also, it's an American project, and they wanted to go to PRL and not Nature. That doesn't explain science. I won't comment on that. Okay, so in the Livingston detector, this is what we saw. So on time, you see it's about 150, 200 milliseconds here. There's a blip of a signal that is rising in frequency and then suddenly disappears. And in Hanford, we saw almost exactly the same signal at almost exactly the same time. And this is characteristic of an in-spiraling compact binary. So two compact objects radiating gravitational waves as they orbit each other will lose orbital energy, and so they will in-spiral until eventually they will merge and form another heavier compact object. And the waveforms that we measure match up very well with the kind of waveforms that we would predict from numerical relativity. So this is the basis of the detection case. This is what it sounds like, the interferometer. So that's the sound of the detection. So you hear the rumbling is the noise, and that sound has been filtered a little bit. You don't hear the sharp lines that we saw in the spectrum, because all then you would hear is just hee, and your human ear would not be able to pick it out. And slightly frequency shifted to make it more audible to human ears, this signal ends at about 250 hertz. And what you see here is the time series on the bottom, and then a time frequency spectrum on the top. So a spectrogram on the top. Hanford on the top and Livingston on the bottom. And now I'll play it again that it's been basically heterodyned up by, I can't remember now if it's 200 or 400 hertz in this video, but more into the center of the human hearing band.
It's a submarine.
Yeah.
Yeah, That's right. It's like a ping. So the hiss you hear is the noise of the detector, but then you can clearly hear the chirp over it. So this is the same waveforms again. And here you see this is the Hanford waveform, and then the Livingston waveform here. And the light red is the Hanford waveform shown on the same plot. So you can see that the two detectors really saw the same signal.
I thought they reversed the up and down.
They are. So the red one has been shifted in time in order to match the light propagation time, and it's flipped up and down because the interferometers are facing like that. So they see the opposite sign. And so this is really the final test that we actually kept track of all the minus signs in the calibration. Because there are a lot, right? There are magnets everywhere, and all of the magnets have, we put all of the magnets in sets of 4 to reduce the dipole moment so that magnetic fields don't couple. And so at some point, you worry if you've missed one of these factors of 2, but this is the proof that we didn't miss the factor of 2, because we had to shift it the way you'd expect it to be. Yeah.
How would you change the detector to detect the other polarization state?
You would rotate it.
In the sense of...
So instead of the arms going like this, you would just put them like this. Yeah. 45.
45.
Yeah.
In the Hanford data, in the residuals, the first tenth of a second looks bigger than the next tenth of a second, or half of a tenth of a second.
Mm-hmm.
Am I seeing something?
I don't think so. I think you're just seeing this little blip right there.
Yeah, that looks like there's a bigger RMS scatter in the first up until 0.3
Yeah.
than there is between 0.3 and 0.35.
And there is some more here in the Livingston detectors. This is just the way the noise behavior works. The noise is not completely stationary in the detectors. So there's always going to be some variations in the RMS. And I'll talk more about how we characterize the non-stationarity and still convince ourselves that the signal is real a bit later. And down on the bottom is the time frequency spectrogram of the two detectors. And in the middle are predictions, reconstructed predictions of what the waveform should look like from numerical relativity and from some of the post-Newtonian templates that we use in the data analysis. Yeah?
Maybe out of sequence, but how long did it take people to realize what you'd found once the signals had been received?
Not very long. Not very long. So they're online triggers. So the idea is that there has been a long push in the collaboration to develop online analyses to see these things as quickly as possible with minutes or tens of minute latencies so that we can send out notices to partner organizations. So we have agreements with partner organizations with follow-up programs to do EM follow-up, radio, optical, and gamma ray X-ray telescopes. And there's been a long push in order to get this done so that we can send follow-ups and send these notices out in a timely manner. So when this was seen, an email was generated automatically and sent to somebody. And then that person, I think they were awake at the time, because the last thing that we were working to do, so you may have heard that the detection didn't happen during our observation run, but happened during our engineering run. And the last thing that we were working on, there were a couple of things. One thing is there would have been a couple of calibration activities, but the main reason the observation run was delayed was to get this system set up and better automated so that people would get woken up instead of just an email going. And that wasn't ready, and that's why it was still in the engineering run.
So do you have a plot of the difference between the two in the upper right?
I don't know, but you can make it. So the data is all available. It's on the LIGO Open Science Center.
Isn't it on any of those 12 papers you said?
The difference?
Yep.
I don't know. I haven't seen that plot. So the sources, and we've been talking about these sources for ground-based detectors for a long time, consist of basically, we group them into 4 classes. And the 4 classes are grouped that way because of the morphology of the signal. So the time frequency morphology. So short, So short signals of known form, known waveform, so increasing frequency, are coalescing compact binary systems. So like neutron star black hole pairs, neutron star pairs, or black hole binary black holes. So these are strong emitters of gravitational waves, and they're well modeled. So we use match template filtering in order to find those sources. And then spinning neutron stars, so pulsars. These are long duration sources that are on all the time, and they're effectively at a single frequency, so we use basically very long Fourier transforms to look for those. Burst sources, which are things that we don't know what they are, just unmodeled transients we call bursts. And there's a long list of things that they could be, but we don't have models for the waveforms. And so we put them in the burst category. And then long-lasting sources, which is basically stochastic gravitational waves. So this is random gravitational waves that are on all the time at more or less constant power. The main source that we've looked for and what we wound up finding was the coalescing compact binary. And it has a characteristic waveform where as the two compact objects are orbiting each other, they emit gravitational waves at a slowly increasing frequency. And as they get closer together, the frequency increases, and so they radiate gravitational waves even stronger. The quadrupole moment, the changing quadrupole moment becomes even stronger. The radiation becomes more rapid, and so they increase in frequency even more powerfully, even more quickly. And so until they merge and something happens, and then they coalesce into a final black hole, and this final black hole is deformed, and it radiates all of its deformities in the form of gravitational radiation. So black holes we think have only mass and spin, but a black hole that is deformed has some other properties besides the mass and spin that describe its space-time. And those properties that cannot be described only by mass and spin wind up getting radiated by gravitational waves. So the search pipelines look for these different classes of sources. And the two that would have found this event that we found are, of course, the transient search, the burst search, because it looks for any kind of transient signal. So it will also find compact binary coalescences. And then, of course, the compact binary coalescence search will find it. And each of those searches has two flagship pipelines. They also have other pipelines, which are independent codes created by different people. And all of the pipelines found the event. But all of the four flagship pipelines found it with similar statistics and similar estimates of the parameters of the source system. So they all make use of the fact that we have two detectors, and you have to see the same signal in both of them. And they all estimate their background, because the noise is not Gaussian. We can't just say that, what is the chance that this would arise from a Gaussian process? If the noise in the detector was completely stationary, you can't do that. You would get the wrong answer. So the way we do it is we time slide the output streams of the two detectors and cross-correlate them and run the analysis pipeline on that time-shifted data. So the data between the two detectors is time-shifted so that we are sure that there is no gravitational wave signal in this time-shifted data, because it wouldn't show up in the two detectors in the two data streams at the same time. But this allows us to characterize the noise transients in both detectors and how those noise transients might, by chance, show up at the same time in both detectors. So this is how we place our limits on the statistical confidence in the detection. When we search using the templates, we create a whole bunch of templates. And so this is a scatter plot showing the masses of the two compact objects in a binary. And you can see what we thought was going to happen here, where things are well filled in. So binary neutron stars, there's a lot. And neutron star black hole binaries, there's a lot. And as you get to high mass black holes, there aren't very many templates out here where we actually found the high mass black hole. So it was quite a surprise. And over here, this shows how sensitive we are in megaparsecs. So for the event that we found, the first event that we found, we would have been sensitive to it at more than 900 megaparsecs. We still could have seen it in the data. And it turned out to be more like 400 megaparsecs away. So it was well and easily seen. That's why you can see it in the time series. This is the plot that shows us why we think it's a real detection. So this is the most important plot, really. What you have on the left here are the statistics of the generic transient search, and on the right are the statistics from the compact binary coalescent search, so the search looking just for in-spiraling compact objects. So the solid plots are the results of the time slides. So when you shift the two detector streams, and you just correlate them and run your search on the shifted data, you know there are no gravitational waves, and you collect statistics on how often high SNR events happen. So this detection statistic on the x-axis is effectively the SNR, and then this is a histogram of how often those things should happen. in whatever time period you've got. So in this case, this is the time period over 38 days. So if you're looking for SNR 8, so there should be 10 of those SNR 8 things. This is not, it's kind of like SNR, but there should be 10 of them in a 38-day period.
Excuse me, could you not move your, we can't see the red point.
Oh,
Can you
sorry.
move more slowly?
So there,
Oh,
yeah, so there is for SNR of 8, and of course, as you move the detection statistic to lower and lower numbers, this line just keeps going up and up and up, and you get more and more and more. So you put some threshold where you expect it to happen, and those are related via a very simple formula to Gaussian-style sigmas. It's like, how long would you have to wait for this to happen by chance? That's how we get the Gaussian-style sigma, and we calculate how long it would wait by using this histogram. And you can see that the event is way out here, so it's way off of the time-shifted data. So that tells us that this event is highly, highly significant and is extremely unlikely to have arisen by noise. And in this binary coalescence search, there are two curves. So there's this black curve with a lot of outliers coming up at low event rate, but a lot of outliers, and then the blue curve coming straight down. The difference between those is that this black curve is exactly what I described to you. It's the two time streams of the detector, two data streams, time shifted, and then you run the analysis. But then once you've found the gravitational wave, once you're sure it's a gravitational wave, a signal, now you have to take that out in order to estimate the significance of other things. Because that one gravitational wave signal will, by chance, correlate with noise transient in the other detector. And that's what you see here. So in order to estimate the significance of other events that might be in the same data set, you have to take out the loudest event first. And then when you take out this loudest event, you get this. So this characterizes something more like the true statistics of the detector that are not polluted. This characterizes the true noise of the detector, so it's not polluted by the signal, the giant signal we found.
So excuse me, you have two red dots that are to the right of the black curve. Does that mean you've seen something at a low signal of noise in addition to the one on the far right?
Yeah, so this one we're claiming, we call that gravitational wave event 15090014, and this one is very close to the black curve, so I wouldn't say anything about that. And this one, I'll let you make your own conclusions as to what that is. But I will say that if you examine it closely, it is also completely compatible with the inspiraling coalescence of two black holes. But we're not claiming it as a detection.
What does LVT stand for?
LIGO Virgo transient. So LVT, you've heard that, that's not on this slide, so you've heard that somewhere else. Oh, it is there, yeah. Yeah, so that's LVT. So that one happened on October 12th. And it's got a signal to noise of roughly 10. So if we hadn't seen this one, we would have agonized and agonized and agonized over whether to claim that as a detection. I don't think we would have, but we might have.
Does that mean there are no other detections that are anywhere near this one that you just reported?
That's right, not in the first 38 days of data. So all of these results are only presenting the first 38 days of data. So this shows the noise sensitivity of initial LIGO in the green curve, and then the red and gray and peach curves here are advanced LIGO, as they were during the first observation run. The dark blue curve is where we hope to be able to get advanced LIGO eventually, so sometime in the next 3 to 5 years after more commissioning breaks and more tuning. And then the cyan curve on the bottom is what you might get from some expected upgrades, some upgrades to advanced LIGO that were not in the original design and have not been funded yet.
Excuse me, about 4 slides ago you talked about the cosmographic background and you talked about the other different sources. And obviously you're maximizing this for 200 hertz.
Yeah.
But you didn't show the frequency dependence of those other sources.
That's right.
Now, would, for example, neutron stars be at higher frequency than the black hole, or would it be just the opposite? I have a hard time understanding where the frequency dependence of those other sources that you're looking for is.
Yeah, so most of the neutron stars that we know about, most of the pulsars that we know about are sitting down here below 100 hertz. And there are a few millisecond pulsars, so we could target those with pushing the sensitivity around 200 hertz, but we don't know where they are. For most of the unmodeled sources, a lot of that would be, we think, at a kilohertz and above. So there is a tension of what you want to search for. And we have decided, in some sense, the whole collaboration has decided, but not just because those are the searches that we want to push for, in part because we knew that there are binary neutron stars out there. So we know that someday we're going to see the in-spiral and merger of two neutron stars.
And that will be lower frequency.
And that's going to, no. So that's going to, this is the sweet spot. This whole thing is the sweet spot. So it's going to in-spiral here, and they're going to merge out here, around 400 or 500 hertz. For the stochastic background, you want to go as low frequency as possible, but we're just limited by being on Earth for that. Yeah?
Can you roughly point out the region and the strain frequency curve where this image lies? So this maximum strain was -21 for this peak,
Yeah.
right?
Mm-hmm.
So would this have been detected in the previous LIGO, and what does it say about the event rate?
So that's what you see here. So here we see the SNR, the way we compute it. So it's the SNR of the whole waveform. So the peak strain was 10 to the minus 21, but this is the power in a 1 hertz band. So this is the amplitude in a 1 hertz band. But it wasn't emitting at 10 to the minus 21 for a second. So it's very hard to compare the peak strain or the energy of the signal and see whether or not you would see it on what is effectively a power spectral density, because they're just different things. So some people plot like the energy spectral density of the signal on these power spectral density plots, and there it sweeps across like this and then kind of comes down like that about 200 hertz. But I don't like that at all, because it's two completely different things that don't have the same units, and people are trying to plot them on the same axes, which is silly, I think. But over here, we can answer your question of whether we would have seen it with initial LIGO. So each of these curves is the SNR, the way we calculate it, as a function of redshift for different detector sensitivities. And the colors match up with this curve, with this plot on the left. So advanced LIGO is this red one here. And initial LIGO is the green one here. And in the past, we have claimed, and we've all had in our heads, and it's been official policy of like, what is the SNR where we would claim detection? And during S6, the most recent observing run with initial LIGO, that number was 8. So if the SNR was more than 8, we would go ahead and start trying to claim detection, and if it's less than 8, we would not. And you can see that this event, this very loud event, would have been below 8 in S6. So we probably would have seen it, and we all would have talked about it, but we wouldn't have claimed detection. Yeah?
How do you know how far it is?
You can get that from the waveform itself. You can get the luminosity distance from the waveform itself. And that's a bit later. I'll talk about that a bit later if we get to it. So here are the states. So here it's inspiraling, and then it merges. And these are pretty accurate. So you see, this is the merger phase where the peak strain is going on. And then here is what looks like a ring down to me, because it's a single frequency and going away. But in reality, what we call the black hole ring down, where it's really a single black hole now just emitting gravitational waves from one dominant quasi-normal mode, is much later in the waveform. And so our SNR for the ring down is actually quite poor. We don't see much of it. We really are seeing the merger and the in-spiral. And this is just some fun stats on the bottom. The green curve is the black hole relative velocity. So it goes up to 0.6 c before they merge. And the separation, this is as they're coming down. So as they get closer, of course, they're getting faster. But it's amazing to think of these two 30 solar mass objects running around each other at half the speed of light. It's pretty scary.
Why does it stop at 0.6?
Well, if they were infinitely compact, I guess it might get up to c, but they have a finite size. Yeah.
Because you have that here. So this looks all perfectly nice, the model view.
Yeah.
But the ones you showed before that actually the fidget
Mm.
signal, they had also...
There's still some wiggles left. Yeah. Those are still noise sitting in the signal effectively. Yeah, so that's one that... Yeah, that's one of the questions that I'm going to have to punt on, because, so to me, this is numerical relativity, and it's just black holes in the vacuum, and so you should get something very clean. And if you take the parameter, and what this is We use the data that we've got and put in the parameters for the black holes and then do a numerical relativity simulation, and this is what you get. The other ones are reconstructed in different ways, so they're Bayesian estimates of what the strain is in the detector. But you're right that it seems like it shouldn't have wiggles. Well, the Bayesian estimates that aren't using the numerical relativity waveforms can have the strain and the wiggles. But it's not clear to me what they say when they say it's numerical relativity reconstruction and it still has some of those wiggles. I don't know where those come from. So I'll have to point you to one of the companion papers. The detail is not in the main detection paper, but it should be in a companion paper.
I've been told many times by people who are doing numerical relativity that the merger part is, oh, we don't know very much about it, it's very complicated. And
It is
when
very
I'm looking at
complicated.
uncertainties on the reconstructed from the template, I don't see any large uncertainties associated with the last moments of the merger.
Yeah, when did people tell you that?
A few years ago, I guess.
A lot's changed.
Really?
A lot's changed. We couldn't make black holes collide in simulation at all. Like the simulation would crash before, I think, 2009. And so there's been extremely rapid progress. Once that problem was solved, the progress was very, very rapid in numerical relativity.
So without being able to calibrate on anything real, they made progress in getting rid of the systematic errors or pretending that they know what they're conditioning on things. How do you know why you're so confident in that if there's no calibration?
How confident on what? Well, because
that's the exact waveform that should produce when you have two black holes merging if we don't have any observations.
How are you confident about any numerical simulation?
You calibrate it with real data.
It converges. You do calibrate it with real data, and this is it. We're providing it. But also, it converges. If it works in the regime where you know it can work, so where you can use the post-Newtonian approximations in the early bit, and then it converges in other regimes, then you can have a lot of confidence in it. It's not calibrated against real data until now. Now we can. But I understand your skepticism, but I think that there are ways to gain some confidence without that final step.
Does the angular momentum of the black holes come into this?
Yeah, it comes into the details of the waveform. But with only two detectors, we can't constrain very well what the angular momentum of the individual components were for this particular event. So this is what we expect the merger rate to be for these events. So this is the event out here at very high SNR. And then if you also count the transient, so this should be LVT, not LVC, the October 12th event. If you also count that as an event and then use those two to derive an event rate, you get a number like this, which is comfortably less than the upper limit that we set with initial LIGO. So that's good. And this is some more of how we are confident in the detectors. So this is a period of weeks on the x-axis. These are terrible plots, I'm sorry. But you should be able to just see these are low SNR glitches in the detector. And the fact that they stay at a constant rate as a function of time is what we mean by saying the detectors were behaving well. So there weren't periods of like excessively glitchy behavior around the detection. So the noise trigger rate is stable, which is what lends us confidence in the time shifting analysis as a valid estimation of noise transients. In addition to just this time shifting analysis to characterize the noise, we also have many, many, many environmental sensors of literally every physical thing that you can think of that someone can measure and that you can buy a measurement device for. And we use those to veto periods of the data when there is some seismic event or a magnetic event or whatever, an airplane flying overhead. These are time series of the SNR of the match templates. So as you run your match template across the data stream, you get a massive peak in the SNR, and it looks great. So what can we learn in terms of astrophysics from a single event? So the first thing is that as best we can tell, there is excellent consistency between the waveform that we observed and numerical relativity, the predictions from GR. And we can also say that from GR, in some sense assuming GR is correct, that such high frequency chirps require extremely compact orbiting objects at very high velocity. And they have to be objects of stellar mass. So essentially what this means is that this is further confirmation that black holes exist. We know that there have been compact objects from luminous X-ray sources. There are compact objects of roughly 15 solar masses in a very small space. But this is a system that exactly matches the predictions and the dynamical predictions of general relativity as far as we can tell. So it's really, in some sense, definitive proof that black holes exist. But even more interesting, it's proof that binary black holes exist, that black holes can form and somehow find each other in binary pairs and merge within a Hubble time. And it's our first test of general relativity in the nonlinear, highly dynamical regime. So I don't know if you've seen this. This is, let's see if we can, I may have to push play here. So this is a numerical relativity simulation of what you would actually see if you were close enough to see it without dying for some reason. I don't think you would survive. I'm not sure what the star field is in the background. It may be the Milky Way. And so this is this is literally what you would see. So I think that this simulation code was actually developed for the movie Interstellar, but it is actual numerical relativity of how the gravitational waves and the warpage of space-time around the two black holes, so there's one black hole there and one black hole there, as they move around each other, how it warps the star field in the background. And this is actually with the parameters of the event that we saw. So I think that's really neat.
That's the Einstein ring we're seeing.
Yeah, yeah. As it jiggles, and it jiggles as the final black hole rings down. So
Who did that?
this was done by a group called Simulating Extreme Spacetimes, and you can find them here. It's a collaboration between about 6 institutions. The only ones I can remember are Cornell and Caltech. This is also from Simulating Extreme Spacetimes, and this shows the black holes on the top here. That just shows you where they are, and then as they orbit around each other, they get closer and closer. The space-time is shown on the bottom. So the deformation there shows you the curvature of space. The color is the rate of flow of time near the black holes. So where it's red, the rate of flow of time has slowed down. And then the arrows show you the flow of space. So effectively like the frame dragging, as space is getting dragged into the black holes and getting dragged around. And as they come, and on the bottom, you see the gravitational waveform. So now they're getting closer and closer, and they're about to inspiral. The frequency is increasing as they come closer together. And at the point of merger, here they merge, and space-time is doing some crazy stuff there, and then the black hole rings down at the end. Yeah?
Yeah, so a question about the 3D orientation of this. Is our line of sight to the black hole parallel or perpendicular to the angular momentum vector of the system?
It should be perpendicular to have seen it as loudly as we
So
did.
we're seeing
I always get confused by what we see of face-on versus edge-on. Yeah.
Is the assumption of it that the orbits have sufficiently circularized in a way that can get as close as these?
Is it really?
Centricity is not an issue.
Is it? Yeah, they will. The orbits will circularize just by radiating gravitational waves. So I don't think you need to invoke any other processes to get that at the point that we can start to see it.
Right, so basically the waveforms are just
Yeah. Yeah. No. Yeah.
At the end of that simulation, you had the merged holes.
Yeah.
And you had green indicating the different time intervals, different distances, or should be.
Different rates of time.
Yeah.
Different rates of flow of time. Yeah.
There was sort of a reddish colour in the middle.
Mhm.
Did that affect the rate of time in the middle, or was that purely spatial curvature?
No, no. So the curvature that you see, that's the warping of space-time, and the color is just the flow of time, the flow of the time coordinate.
You've got different colours.
Yeah.
So you're looking at different rates.
Yeah, in different gravitational fields. This is just like here, and this is necessary to make GPS work, even on Earth. Yeah.
Does the chirp and the measurement of this tell you anything about give you an upper limit on how massive any accretion disks could be that are around either one of these or both of them?
Well, that's a good question. I don't know. We don't expect accretion disks around black holes of 30 solar mass.
Who does?
We don't. I don't know who But the yeah, I don't know how much the waveform constrains that. So these are the estimates of the masses of the object. So one is roughly 36 solar masses, and these are in the source frame, and one is roughly 29 solar masses. And what we can actually get from the waveform is not the masses individually, but the phase evolution gives us the chirp mass very well. And then from the frequency of the merger, so that's the complicated part that you really need numerical relativity for, you can get the total mass. And so from this, we can now infer the component masses by having both the chirp mass and the total mass. The luminosity distance also comes out of the waveform. But we don't constrain it very well. So we quote this number of like 400 megaparsecs, but we don't constrain it very well because we can only get one polarization. So in order to really constrain it, we would need more detectors. There's a strong degeneracy, and so poor measurement of the luminosity distance. The final black hole mass, we think is about 62 solar masses, which means 3 solar masses were radiated during the collision. So, and that's the difference between the mass at t equals minus infinity and the mass after the collision. So it's the parameters of the waveform, and that's if you had a numerical relativity simulation starting with 29 and 36 solar mass black holes and brought them together from infinity and they radiated, that would radiate 3 solar masses of energy in the form of gravitational waves. But most of that happens during the ring down. And so the peak luminosity is roughly 10 to the 54 ergs per second, a little bit more. So that's more than all of the stellar luminosity of the universe. So it's a lot of power. Yeah. But space-time is very stiff, and so it doesn't make a big difference to us here. But I think someone calculated that it works out to something like 0.01 watts per meter squared at Earth of energy flux from gravitational waves for something that a single event that was 1.3 or 1.2 gigalight years away.
So can't you work out the luminosity independently from the gravitational waveform, or from the flux of gravitational waves?
From the if you knew the polarization, but we don't know the polarization.
But how big a factor is that?
Well, big enough to make these error bars. So this is how well we can constrain it, but that's a pretty big error bar.
But if you had another Virgo, like a Virgo working at this time, wouldn't that give you the polarization?
Yes.
And so you could.
And then we tell much better. Yes. Yeah. So this is only because this massive error bar in the luminosity distance is only because we have 2 detectors and they're aligned to see the same polarization. So the source sky localization is not very good with only 2 detectors because you only have the line of sight and then some weak constraint on the polarization. And so there's this 600 square degree, 90% probability region. Nonetheless, we sent out an alert to our EM astronomers after 2 days after we saw the event, instead of, like the 10 minutes that we would like it to be. And I think 22 different partner organizations imaged the region of the sky out of, I think there are 65 that we have agreements with, and 22 took pictures. And you may have heard that the Fermi gamma ray burst monitor saw something at exactly that time, a very small excess of kilovolt. Yeah, I think like KeV photons. So that may have been an EM counterpart, which presumably would be from accretion disks around these black holes. But the false alarm probability is 0.2%, and we'll see what they say about that.
Where was
But
their
pretty much spot in the middle there of our uncertainty region.
And it's that small? As small as that inner yellow, for example?
Oh yeah, I think so. I think so, yeah. But they have quite a large field of view, which is why they were able to see it. Because we told them about the event days later, but they looked back through the data because they're basically scanning the whole sky. So their sky localization is also quite poor for an event that was of such low energy. It was a very, very tiny event, and they would never have claimed it as anything if it had not been coincident with this trigger. So this is some of the different kinds of where we would expect the various triggers to see. So days later, we would expect some radio emission and optical afterglow from minutes to days, and gamma rays you would expect to happen immediately after the merger. So these are the gravitational wave observatories around the world. So the two operating advanced detectors are the LIGO ones in Hanford and Livingston. There's one in Virgo, which is currently being upgraded, and we expect it to come online later this year, so that will give us a third detector. GEO is more of a prototype because its arms are just too short. Kagra is a Japanese detector being built in a mountain, so they've finished excavating the 3-kilometer tunnels in the mountain, and they're putting in the vacuum tubes and putting in some optics. LIGO India is literally a LIGO interferometer, which we will install in India, and that was just approved by the cabinet of India 2 days ago, or maybe it was yesterday. So it actually looks like it will happen. So that's very exciting. And so the last thing you may be interested in is tests of consistency with general relativity. So the main thing that I guess I want to point out here is these are the post-Newtonian orders and how well, you can't see on the left, but they're all roughly 100%, like the variability, the relative fraction of variability that we can see in post-Newtonian expansions of the waveform versus what you would get from general relativity is at this level of roughly 100%, which is worse than a binary pulsar, which has the best constraint at 0th Newtonian order, but the pulsar doesn't do very well at anything higher than 0th order, and so this becomes the best constraint at higher Newtonian orders that we have to date. I don't know what happened. It used to show the whole slide. Yeah. Yeah. So we'll just zoom in.
You could just,
It says here,
No.
go back,
showing the whole screen. Yeah. I guess it's getting
press the green plus.
No, that's not the whole screen.
Yeah, but it'll be close enough.
Yeah. So the mass of the graviton we constrain, or the Compton wavelength of the graviton now we constrain to longer than 10 to the 13 kilometers, which is only a tiny bit better than you get from the solar system. So this yellow bit is the solar system constraints, and then this red bit is what we got from this event.
I thought the mass of the graviton is 0 since it's moving to speed of light.
Yeah. 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 It's an upper limit on what we expect to be 0. So this is a slightly better upper limit than we had before from the fact that the solar system matches general relativity, and the blue is what you get from the same binary pulsar that set the other constraints in the previous slide. And from a single event, there are a couple of ways that binary black holes we think might be able to form. One is Kalman envelope, so 2 massive stars both undergo core collapse supernova down to black holes, or more smaller objects dynamically capture and grow larger and larger black holes, and then those 2 black holes find each other in dense environments. With one event, we can't really tell the difference. But it is the first observation of a black hole with a mass larger, convincing observation of a black hole with a mass larger than about, not counting supermassive black holes, but stellar mass black holes larger than about 15 or 20. So it's in some sense confirmation that there are some very low metallicity environments with some large suns out there. Okay, so I think that's all I wanted to say. There's more plans for the future. We are here in advanced LIGO, and we have a roadmap of 3rd generation detectors and beyond, and this includes space interferometers like LISA and DeSiGo. So thank you for your time.